Hello everyone, welcome to this session. So, by now we have studied single ended ring oscillator, zero differential ring oscillator which gives you phases, IQ phases, okay. And both these oscillators, their frequency can be controlled. So, by changing their supply voltage, we have seen previously that by controlling the current of the oscillator or designing the inverter as a current stopped inverter, you can control their output frequency. Now, we are going to deal with this frequency control in little bit more detail. Okay. So, just as an example, I am going to just draw a symbol for the VCO, which is like this, and here this supply is VDD VCO. Now, whether you control VDD VCO using current source or voltage source, that is your choice, and this is your output. Any one of the nodes of the oscillator can be chosen as an output. If you want multiple phases, you will take multiple phases in output. This oscillator can be a simple inverter, 3 inverters in the ring, which is odd number of inverters, or you can have pseudo differential ring oscillator also. Okay. So, this is just to tell you that any of these blocks can be, the oscillator can be any of these blocks. Okay. Now, well, you need to have cross couple inverter here to connect it. Okay. So, these are the two oscillators which we are considering. Now, the supply of these two oscillators, which is VDD, right, this is VDD VCO, and similarly you have VDD VCO for the bottom oscillator. Now, what we want to do is we want to control the frequency of the oscillator by controlling VDD VCO, because we know that when you have an inverter connected to you designed an inverter and you have this voltage as VDD VCO. By the way, the parasitic capacitance which you are going to have, that is fixed, right. So, the charge and the discharge rate, charging rate through PMOS and discharging rate through NMOS depends on the gate overdrive for PMOS and similarly gate overdrive for NMOS. Now, gate overdrive for PMOS and gate overdrive for NMOS, that depends on the supply voltage. When I say gate overdrive means VSG minus mod VTP for PMOS and VGS minus VTN for NMOS. Okay. So, this is valid that if you vary the supply of the inverter, you are going to vary the delay of the inverter. And what delay we are talking about? We are talking about midpoint to midpoint, zero crossing point, midpoint zero crossing. So, if I give this input and the output, this is the delay which we are talking about. Okay. So, what happens is that in order to vary or we know that if we vary VDD VCO, we can control the frequency of the oscillator. Now, if this particular oscillator is used in the PLL with the help of the loop filter, then what you have is the loop filter is something like this, RC1 C2, and this normally we use the V control voltage to control the frequency of the oscillator. If you recall the PLL block, well, one way you can say is, oh, that is, if that is the case, I can very well go and connect the oscillator to this, so that I can vary the frequency. Okay. But this is not feasible, because oscillator draws a certain amount of current, and if I take the DC current out from the loop filter, then I am discharging the control voltage of the loop filter, because the charge pump which connects to the loop filter This particular charge pump gives the current to the loop filter once in a reference cycle. So, whenever you get up and down pulses which control these switches, they are turned off, there is no current coming from the charge pump, and the current required by the VCO will be taken from the capacitor. So, your control voltage will keep on changing a lot and your frequency will vary. So, this is not the solution. So, one way to supply the current to the oscillator without discharging the loop filter is the following. We have seen that thing previously also. So, we can have a current source, you can have an NMOS control current, PMOS control current source like this is VDD, and this voltage we hope it will be VDD VCO such that I get I VCO current for a given output at frequency f oscillator. Okay. And this voltage is V control, and this V control can be connected to the loop filter. So, in this case, if you look at it, our VDD VCO. So, first thing we should understand that f oscillator is going to be proportional to VDD VCO, right. In order that this PMOS acts as a current source, the PMOS acts as a current source when it operates in saturation region. So, the condition for the saturation region is that VDD minus VDD VCO, this is VSD, should be greater than equal to VSG minus mod VTP. Okay. This implies that your VDD VCO is less than equal to V control plus mod VTP. Okay. So, because your output supply voltage is this particular supply voltage is less than equal to V control plus mod VTP, right, you will have the limit on the frequency. Well, that is what you have. So, this is one way of controlling the oscillator and supplying the current required for the oscillator. Similarly, you can control the way you controlled your control the current through the oscillator like this. You can also control it by using an NMOS. Okay. So, in place of PMOS, let us say if I use NMOS. So, this is V control. Okay. I will choose my V control in such a way that I get the desired VDD VCO and I VCO that I will have. Now, here the thing is that the NMOS, if NMOS operates as a current source, it should operate in saturation region, which means that VDD minus VDD VCO, this is VDS, right. This should be greater than VGS minus VTN. So, here the only thing which we may need to make sure is that your VDD is greater than V control minus VTN. Okay, that is one condition. The problem here is if you try to increase your VDD VCO, okay, then what you will see is that your VGS minus VTH for the NMOS transistor will be 0. So, what we need is we need V control minus VDD VCO, this is VGS minus VTN should be greater than equal to 0, which means that VDD VCO is less than equal to V control minus VTN. Okay. And you know from here that V control is to keep the transistor in saturation region, your V control is actually less than equal to VDD plus VTN, right. So, You can plug that in that okay, V control is VDD plus VTN, but think about it, you are using this transistor in a given supply for a given supply voltage, right. So, V control will automatically be limited by VDD. You cannot have V control larger than VDD. If V control is not larger than VDD, then VDD VCO is less than equal to VDD minus VTN. You compare these two conditions, that in one case your VDD VCO, right, here also the same relationship will be there for V control. What is that? That VDD minus V control minus, here V control can go to 0 by the way. So, because the PMOS minus mod VTP, this should be greater than equal to 0 to keep the PMOS transistor on, which means that V control is less than equal to VDD minus mod VTP. Okay. So, what we see in this particular case is that here VDD VCO is limited by V control minus VTH or VDD minus VTN. VDD VCO is limited by this. In the previous case, your VDD VCO is limited by again VDD. Okay. So, if you substitute this here, then you will see that VDD VCO at max can go to VDD, but if this depending on a VDD VCO I push this to VDD, then what will happen is these transistors will appear into linear region. So, for PMOS it is the case, if you keep on reducing the overdrive, then your VDD VCO can keep on increasing, but in that case the size of this transistor will be very large. So, practically that is not possible. In case of NMOS, what you see here is that you have an upper limit VDD minus VTN, which is a problem. Okay. So, in this case you are limited by your VDD VCO is limited by the headroom which you want for the PMOS transistor, and this headroom you can say is effectively the gate overdrive of the PMOS transistor, gate overdrive VGS minus VTH. Okay. So, this can be depending on which process you are using, this can be 100, 200 or 300 millivolts, whichever you want. So, if we want to increase the VCO frequency, we want to maximize this, but there is a upper limit that we have to maintain VDS to first order the equal to overdrive of the PMOS transistor. Okay. So, VDD VCO is limited by VDD minus gate overdrive of PMOS. Okay. In the second case, your VDD VCO is actually limited, there is a upper limit, VDD VCO is limited by VDD minus VTH. Okay. Normally, sorry, VTN I am using for threshold voltage of NMOS transistor. Normally, threshold voltage of NMOS transistor is larger than the gate overdrive which you can use for biasing PMOS, because gate overdrive is in your control, right. So, if you keep gate overdrive at 100 millivolts, you can do that while you are having a threshold voltage of 300 or 400 millivolts. So, normally the headroom for the VCO in case of NMOS control is smaller than in the case of PMOS control. So, if you want to have a higher frequency, then this is the preferred choice. So, if this is the preferred choice, why am I discussing both of them? Well, the reason is that one of the other performance metrics of the oscillator which we have not discussed so far for this case is power supply rejection. So, if you take both the cases, the one which you have with respect to PMOS, and try to find out that how the supply noise is going to affect the oscillator, Okay, this is the oscillator, and I have this. I am just calling this node as VDD VCO. There is no specific voltage source connected. Okay, don't get mistaken by that. So, this is V control, and I have the supply voltage. So, let us say I am modeling the supply voltage with some noise small VDD and whatever capital VDD you need. In order to find how the supply noise is going to affect my VCO frequency or the phase noise later, I can find out how the supply noise affects my VDD VCO. Okay. And because this is noise, I can use noise which is small in magnitude. I can use a small signal model of this circuit. So, to begin with, I am going to model my VCO which has an operating point. This is just an example. It has a voltage VDD VCO, it has the current I VCO. So, I can effectively model this with a resistance. This is just a modeling whose R VCO is equal to VDD VCO DC value of the resistance I am having divided by I VCO. This is just for modeling purpose. Okay. And this node I will call as a small VDD VCO, a small signal voltage. For PMOS transistor we all know. So, using this circuit for the small signal modeling, I will have GMP here, GMP minus GMP small VDD, because control voltage you are not looking at the change in the output frequency with respect to the control voltage, you are looking at the change in the output frequency or the supply of the oscillator with respect to the supply voltage. Okay. So, you are going to have RDSP, the resistance of the PMOS transistor, modeled by resistance of the voltage control oscillator. Okay. I have, this is only to calculate the DC gain. I have neglected the capacitors right now. We can take that into account while making the system more complicated sometime later. So, this is a small VDD. This node, as I said, is a small VDD VCO. So, using this, I need to find out what is a small signal VDD VCO divided by small VDD. This will tell us how the supply noise is going to change the VDD VCO, and we know if you change VDD VCO, your frequency of the oscillator will change from our analysis for the delay part. Okay. So, if we find this, this will help us to find the supply noise rejection. So, in order to find this, I will solve the circuit as shown, small signal circuit, which is VDD VCO by R VCO, so current in this branch, plus VDD VCO minus VDD divided by R DSP, which is the current in this branch, minus GMP. So, the current in this branch is your minus GMP VDD equal to 0, right. So, well, you can take all the terms on one side. So, we have VDD VCO 1 by R VCO plus 1 by R DSP equal to 1 by R DSP plus GMP times VDD. Okay. So, this parameter which you are seeing here, I can just write it directly now. This is equal to 1 plus GMP times R DSP divided by 1 plus R DSP divided by R VCO. So, this is the gain which you get. Okay. So, approximately if GMP RDSP, which is the gain of this transistor, is quite large, you can write it like this, and this is 1 plus RDSP by R VCO. If GMP RDSP is quite large, then you see that VDD VCO by VDD that becomes quite large. Okay. So, you have depending on what is your GMP and all, you will get your supply noise, which is a small VDD, is passed to VDD VCO. We have to compare this thing with our NMOS case. Okay. So, what happens in case of NMOS? You have this, and then your VCO, this using the small signal model for the NMOS and your VCO, we can write it like this or draw it in this manner. You have RDSN and you have this as RVCO. Okay. This is GMN times VDD VCO, by the way, minus GMN times VDD VCO, and you are applying the supply noise here, small signal, right. So, we have minus GMN times VDD VCO plus VDD minus VDD VCO by RDSN equal to VDD VCO by RVCO. Okay. You take the terms on one side. So, what you will get here is VDD into 1 by or just VDD as VDD VCO into RDSN by RVCO, this is a multiplication, plus GMN RDSN plus 1. So, VDD VCO divided by VDD is 1 divided by 1 plus RDSN by RVCO plus GMN RDSN. Okay. GMN RDSN is the gain of the transistor, similar to what you have GMP times RDSP. So, if you compare the two cases, what you will see is the large part of the gain, which is your GMN RDSN. In one case it is coming in the numerator, other case it is coming in the denominator, right. So, wherever you have in the denominator, that will help us to suppress the supply noise coming to the VDD VCO. So, this is surely it depends on the exact value, but this is typically much lesser than 1, whereas this can be greater than 1, can be much greater than 1 if required or if designed that way. So, you will have a lot of DC gain when you use PMOS as compared to NMOS. Okay. So, if you want to suppress the supply noise to the oscillator supply, you would prefer to use NMOS, but you run in the problem of upper limit on the frequency. So, based on your requirements, you have to trade off one with the other. Either you can have the highest frequency in a given process, or you can have a better supply noise rejection, at least for these two methods. Okay. We will see other methods in the next session. Thank you.